Hello friends, I welcome you to part 2 of solved past paper questions in electric fields. IBM is my name and I hope you're going to enjoy the second part of solved past paper questions. This will be the last part of uniform electric field, and therefore in part 3 and part 4 I'm sure we shall be dealing with a non-uniform electric field. So enjoy, don't forget to subscribe, share and like, comment on this video as you wish. You can also write to me and raise your questions. I will always try my level best to answer them. So let us start from where we stopped. I have some cough, but I know I will manage this. So let us start from where we stopped yesterday. So yesterday we were supposed to continue with this question here. So I want us to start directly from this point. So an electron traveling horizontally in a vacuum enters the region between two horizontal plates as shown. So the upper plate is at positive potential and the bottom plate is at zero potential because it is actually earthed. It is connected to the earth. The lower point is earth, the upper plate is at positive 4. The electric field between the plates may be assumed to be uniform and outside the plates to be 0. On the figure 6.1, draw an arrow at P to show the direction of the force on the electron due to the electric field between the plates. So we know that field lines originate from high potential to low potential. These are field lines from high potential to low potential, and they are supposed to be parallel and equally spaced. But when an electron enters, an electron experiences a force in the opposite direction to the field. So the electron at point P will experience a force in that direction, so that will be the force due to the electric field. So the arrow will be upwards because a negatively charged particle experiences a force in the opposite direction to the field. Then sketch the path of the electron as it passes between the plates and beyond them. So since it experiences a force upwards, therefore the path will be parabolic. I don't know if I can draw this very well, but the path will be parabolic. The path will be parabolic towards the upper plate. And of course, when it emerges from the upper plate, the line will now be a straight line, which will be a tangent to that path. So here you have to draw a perfect straight line. When it emerges from the plates, this part here is supposed to be a straight line because there is no field, there is no electric field outside the plate. So here you put a ruler and draw a perfect straight line. You draw a perfect straight line outside the field. But inside you see it is a curve, or it curves towards the top plate. So that will be the path of the electron. Then determine the electric field strength E between the plates. Determine the electric field strength between the plates E. So we go back to the plates, we notice that the PD is 400 and the separation between the plates is 0.8 centimeters. So we shall simply say electric field strength E is going to be equal to V over D, that will be 400 over the distance between the plates, which is 8 centimeters. Is it 8 centimeters? 0.8 centimeters. So this will be 0.8 times 10 power negative 2. And when I press the calculator very quickly, this is 5.0 times 10 power 4. Calculate for the electron between the plates the magnitude of the force. The force due to a charged particle in an electric field is the charge times the electric field strength. The charge of the electron is 1.6 times 10 power negative 19. The electric field strength is 5.0 times 10 power 4. So this is giving me, of course, 5 times 1.6 is 8. So this is 8.0 times 10 power negative 15. So that is the force. Its acceleration, since force is mass times acceleration, then the acceleration is going to be the force over the mass. And this will be equal to 8.0 times 10 power negative 15 divided by the mass, which is 9.11 times 10 power negative 31. Then I press my calculator. My calculator gives me 8.8 times 10 power 15 meters per second squared as the acceleration. State and explain the effect, if any, of this electric field on the horizontal component of the motion. State and explain, if any, of this electric field on the horizontal component of the motion of the electron. On the horizontal component of the motion of the electron. So we notice that the electric field is acting vertically. By all means, since it is acting vertically, it is acting normal to the horizontal. Therefore, it will not have any effect. So we can say, because, I don't want to write because like this. So because the electric force is normal to the horizontal motion, then it has no effect. So the electric field acting normally to the horizontal motion cannot have an effect in the horizontal. Next, two oppositely charged parallel metal plates are situated in a vacuum as shown. Negatively charged plate is on the top, positively charged plate is on the bottom. Note that is a positively charged particle. Field lines are vertically upwards. Field lines are from high potential to low potential. And a positively charged particle experiences a force in the same direction as the field. So everything is given here. The plates have length L. The uniform electric field between the plates has magnitude E. The electric field outside the plates is 0. A positively charged particle has a mass m and a charge positive q. Before the particle reaches the region between the plates, it is traveling with the speed v parallel to the plates. The particle passes between the plates and into the region beyond them. On the figure, draw the path of the particle between the plates and beyond. So because it is a positively charged particle, it experiences a force in the field towards the top plate. So the path will be parabolic. The path of the particle will be parabolic towards the top plate. A smooth curve, a smooth curve towards the top plate. And when it emerges, it must be a straight line. A smooth curve towards the top plate. And when the particle emerges, this should be a straight line. So here you put a ruler at the point of emerging, then it should draw a tangent to that straight line. You draw a tangent to the curve, So I will draw a tangent to the curve so that when the electron emerges, when the charged particle emerges, this part here is supposed to be a straight line. So that should be a straight line. Okay, so that is the path of the positively charged particle. It experiences a force towards the top plate. That is because it moves in the same direction as the electric field. Next, For the particle in the region between the plates, state expressions in terms of E, M, Q, V, and L as appropriate for the force. Note that E is force per unit charge. Therefore, it means the force is going to be charge Q times E, as simple as that. Then the time T for the plates to cross the region. The time T for the particle to cross the region between the plates. So if we consider horizontal motion, S is equal to ut plus a half at squared. There is no resultant force in the horizontal, so the acceleration is 0, so that part will be 0. Displacement in the horizontal is L, initial velocity is V, and then the time will be T. So T will therefore be L over V, where L is the length of the plates. So here, our answer T is going to be equal to L divided by V. State the law of conservation of linear momentum. We know that for an isolated system of interacting bodies, the total momentum remains constant. For an isolated system of interacting bodies, the total momentum is always constant. What we mean by an isolated system of interacting bodies is a system of bodies where there is no external resultant force acting on them. So the total momentum before they interact is the same as total momentum before that is after they have interacted. Part 2, use your answers in A, Roman 2, to state an expression for the change in momentum. We know that force is defined as the rate of change in momentum, that is change in momentum with time. That means change in momentum is going to be the force times time. So when we multiply the force times time from above, we are going to realize that the change in momentum is actually going to be equal to E times Q times L over V. That is force times time. Part 3. Suggest and explain whether the law of conservation of linear momentum applies to the particle moving between the plates. Well, there are two ways of thinking about this. Number one, we can think of the particle alone, and if we think of the particle alone, it is not isolated because there is an electric field which is exerting a force on the particle. So it means the particle alone is not an isolated system. So if the charged particle is not an isolated system, then the law of conservation of linear momentum does not apply. That's one way. The second way, we can look at the system to be the particle and the plates. The particle and the plates. When a particle interacts with the plate, it exerts a force on the plate, and the plate must be exerting an equal but opposite force onto the particle. Therefore, in that case, the resultant would be 0. So we can say in that case, the law of conservation of momentum applies. So for the first case, the charged particle is not an isolated system. The charged particle alone is not an isolated system, so the law does not apply. Alternatively, we could also think of the system to be the particle and the plates. So if the system is the particle and the plates, if the system is particle and the plates, then equal and opposite change in momentum occurs on the plates. So there is equal and opposite change in momentum on the plates. Let me say there is equal and opposite change in momentum on the plates. And so in this case, when we define the system to be the particle and the plate, so in this case the law applies. As simple as that. Okay, next. Two parallel vertical plates are connected to a power supply as shown. The separation of the plates is 16 millimeters. On the figure, draw at least 6 field lines to represent the electric field between the plates. Field lines originate from high potential to low potential. This plate is positive, the other plate is negative. So at least 6 field lines, they should be straight lines which are parallel to each other and ensure that they are equally spaced. I can't do that without a ruler easily on the tablet, so you can draw yours. Extremely parallel and equally spaced. Extremely parallel and equally spaced. The arrows should be pointing from left to right because field lines originate from high potential to low potential. An alpha particle travels in a vacuum between the two plates. The electric field does work on the alpha particle. The gain in kinetic energy of the particle is 15 kilovolts. The gain in kinetic energy is 15 kilovolts. Calculate the electric field strength between the plates. The electric field does work on the alpha particle. The gain in kinetic energy is that. So calculate the electric field strength between the plates. So first of all, the particle is an alpha particle whose charge, the charge of an alpha particle, the charge is 2e. That's number one. Number two, we know that the gain in kinetic energy, is equal to the charge times accelerating PD. That's number two. And remember that the charge is 2e. So the gain in kinetic energy, which has been given as 15 kilovolts, is going to be equal to charge times PD. That means we have an idea of the PD. Therefore, since we know that electric field strength is equal to V over D, then we can now just simply substitute. If we can equate this to the kinetic energy, which is 150 times 10 power 3, that is to change it from kilovolts to kilo electron volts to electron volts, then times 1.6 times 10 power negative 19 to change it from electron volts to joules. This will give us the potential difference V. And if you try to make V the subject from here, you see that V is going to be, this will be 15 times 10 power 3 times 1.6 times 10 power negative 19 divided by the charge. Your charge is 2e, so this will be 2 times 1.6 times 10 power negative 19. And when you press your calculator here, it gives you V as so V is 7,500 volts. That is V. But I want E, so E is going to be equal to V over D, which will be 7,500 divided by D, which is D is 16 millimeters. So that will be 16 times 10 power negative 3. So this is giving me 4.7 times 10 power 5. 4.7 times 10 power 5 volts per meter. Alternatively, somebody would think about the equations of motion. So using kinetic energy, somebody would find the speed, because kinetic energy EK, I'm just giving an alternative somewhere here. The kinetic energy EK is going to be a half mv squared, which will be Q times V. And the kinetic energy has been given, so I'm just going to find V. V is going to be equal to, I will just press the calculator because the kinetic energy I've already converted it here. Sorry. So V is 8.5 times 10 power 5 meters per second. When you equate kinetic energy equal to half mv squared to the value of kinetic energy, you will get V as that. Then from the equations of motion, V squared is equal to U squared plus 2as. This equation will help you to find the acceleration. So the acceleration is going to be V squared. If it started from rest, initial is 0. So the acceleration is going to be V squared divided by 2s. That is V squared over 2s. And when I substitute, since V squared is this, V is that, distance, displacement is 16. So that would be 8.5 times 10 power 5 divided by 2 times 16 times 10 power negative 3. The acceleration here would be 2.25 times 10 power 13 meters per second squared. Now I could again now find E from force over charge, which is MA over charge, which will be, of course, here now you'll be able to think about the mass of an alpha particle, which is 4 times U. M is 4U, where U is the unified atomic mass unit, so that would be 4 times 1.66 times 10 power negative 27, then times the acceleration which we have above, divided by the charge, which is 2 times 1.66 times 10 power negative 19. You will get approximately the same value of E. So you see how long this would be, and it would require you to know more concepts. It would require you to know more concepts, equations of motion, mass of an alpha particle, and so on and so forth. Next, so you can press your calculator and verify if it brings you back to the same thing. Two horizontal metal plates are 20 millimeters apart. In a vacuum, a PD of 1.5 kilovolts is applied across the plates. A charged oil drop of mass 5.0 times 10 power negative 15 is held stationary by the electric field. On the figure, draw lines to represent the electric field between the plates. So upper plate is at high potential, lower plate is at low potential, so the field lines point downwards. Note that they should be equally spaced and parallel to each other, so they should be pointing downwards. Equally spaced, parallel to each other. That is the electric field. That will be the electric field. The next part, part 2. Calculate the electric field strength between the plates. We already know that E is V over D, and V is 1.5 kilovolts, so that will be 1,500. The separation was 20 millimeters, so this will be 20 times 10 power negative 3. And when I press my calculator, so this is 75,000. 75,000. Calculate the charge on the oil drop. We know that force is equal to charge times electric field strength. And we also know that the weight of the oil drop will be equal to mg, because they say it is held stationary by the electric field. So that means the charge times the electric field strength must be equal to m times g, because there are two forces acting here. The weight is acting downwards, and since if it is stationary, then there should be a force acting upwards. And that also gives me an idea that the oil drop must be negative if the force is to act in the opposite direction to the field. Therefore, the charge is going to be mg divided by E, which will be equal to 5 times 10 power negative 15 times 9.81 divided by 75,000. And when I press my calculator, When I press my calculator, this is giving me 6.5 times 10 power negative 19. And this charge is going to be negative. How do I tell that the charge is negative? Normally, the weight will act vertically downwards. If the oil drop remains stationary, there should be a force balancing the weight upwards. But the field is downwards. The only sign of charge which experiences a force in the opposite direction to the field is a negative charge. Therefore, this charge here must be negative. That charge must be negative. So the potential of the upper plate is increased. Describe and explain the subsequent motion of the drop. So if the potential of the upper plate is increased, it means the electric field strength has been increased. That means now the force due to the electric field is going to be greater than the force due to the gravitational field. So the force due to the electric field is now greater than mg, and that means the resultant force is upwards. So it means the upward force is now greater, or we can say F due to the electric field is now greater, so the resultant force is upwards. And if the resultant is upwards, it means the drop will move upwards. Okay, as simple as that. A uniform electric field is produced by applying a potential difference of 1200 volts across two parallel metal plates in a vacuum, as shown. The separation is 14 millimeters. A particle P with a charge of 3.2 and mass of 6.6 starts from rest at the lower plate and is moved vertically to the top plate by the electric field. Calculate the electric field strength. That one is easy. E is equal to V over D, which is going to be equal to 1200 divided by D, which was 14 times 10 power negative 3. Change it to meters. When I press my calculator, so this is giving me 8.57 times 10 power 4 volts per meter. The work done on P, if it moves from P, from that point to the other point, the work done is easy. Work done is equal to force times distance. But force in an electric field is charge times electric field strength, then times distance. But electric field strength can also be V over D, then times distance. That means the work done is simply Q times V. And if that is true, we just say the work done will be equal to the charge, which is 3.2. The charge was 3.2 times 10 power negative 19 times the PD, which is 1200. And when I press my calculator, I am getting 3.84 times 10 power negative 16. 3.84 times 10 power negative 15 as the work done. The gain in gravitational potential energy, okay, so gain in gravitational potential energy, this is 14 millimeters. I will use the gain in gravitational potential energy. I will use U for potential energy. So the gain in gravitational potential energy will be mgh, which will be the mass was given as 6.6 times 10 power negative 27. You can check on the question. G is 9.81 and H is 14 times 10 power negative 3. I press my calculator. And this is giving me 3. This is giving me 3. No, how did I calculate this? Okay, this is giving me 9.06 times 10 power negative 28 as the gain in gravitational potential energy, the gain in potential energy. Then the gain in kinetic energy, I will simply call it EK. Of course, gain in kinetic energy is a half mv squared, which will be equal to, of course, 3.8 times 10 power negative 16. The gain in kinetic energy, sorry, this is not true. Something is disturbing me. The gain in kinetic energy is going to be now that if the the work done must be equal to the gain in potential energy and the gain in kinetic energy. So the gain in kinetic energy is going to most likely be equal to the work done, which is 3.8, 4 times 10 power negative 16 minus the gain in potential energy, which is 9.0 times 10 power negative 28. Of course, this is a very, very small value compared to the other one. So most likely the gain in kinetic energy is almost 3.84 times 10 power negative 16 joules. Then the speed of P when it reaches the top plate. The speed. Now that I have the gain in kinetic energy, I can easily estimate the speed. I can easily estimate the speed of the particle when it reaches the top plate. So EK is equal to a half mv squared, and this is going to be equal to 3.84 times 10 power negative 16. So it means V is going to be 2 times 3.84 times 10 power negative 16 divided by the mass, which is 6.6 times 10 power negative 27 under the square root. So this is giving me 3.4 times 10 power 5 meters per second. Two horizontal metal plates are connected to a power supply as shown. The top plate is at 1.2 kilovolts, or the potential difference is positive 1.2 kilovolts. The separation is 40 millimeters. The switch S is then closed so that the potential difference is 1.2. On the figure, draw 6 field lines. So field lines originate from high potential to low potential. Being a uniform field, the field lines will be parallel to each other and equally spaced. Parallel to each other and equally spaced. You can use a ruler to draw field lines which are parallel, extremely parallel to each other. Me, I'm using a free hand. So the field lines point downwards from high potential to low potential. They are parallel and equally spaced. Use a ruler to draw very neat field lines, equally spaced and from high potential to low potential. Calculate the electric field strength E between the plates. So we want E between the plates, but V is 1.2 kilovolts. So E is going to be V divided by D, which is the same as 1200 divided by D, which is 40 times 10 power negative 3. And this is giving me 3.0 times 10 power 4 volts per meter. The switch is opened and the plates lose their charge. Two very small metal spheres A and B joined by an insulating rod are placed between the metal plates as shown. Sphere A has a charge, negative E, and sphere B has a charge, positive E, where E is the charge of a proton. The length AB is 15 millimeters. The rod is supported at its center C so that the rod is horizontal and in equilibrium. The switch S is then now closed so that the potential difference is again 1.2. There is a force acting on A due to the electric field between the plates. Show that the force is that. Force due to the electric field is the charge times the electric field strength. The charge is 1.6 times 10 power negative 19 because it's an electron. The electric field strength, we have already calculated it above, to 3.0 times 10 power 4. Pressing the calculator just to verify. So pressing the calculator gives us 4.8 times 10 power negative 15 as the force. The insulating rod joining A and B is fixed in the position as shown. Calculate the torque of the couple acting on the rod. So torque of a couple is the moment of a couple. This is acting vertically downwards, and there must be a force acting vertically upwards. These two forces constitute what we call a couple. So that means the resultant moment is going to be clockwise. So since we know one of the forces, moment of a couple is the product of one of the forces and the perpendicular distance between the two forces. So the couple, which is the torque of a couple, is equal to the force times the separation of the charges, or separation of the forces. And this will be equal to 4.8 times 10 power negative 15, then times the separation of the charges, which is 15 millimeters. So this will be 15 times 10 power negative 3. And when I press my calculator, this is giving me 7.2 times 10 power negative 17. I converted all the units, so the unit here will be Newton meters. The insulating rod is now released so that it is free to rotate about C. State and explain the position of the rod when it comes to rest. Of course, when it comes to rest, if it's allowed to rotate, then it will go vertical. So it will be like this. The rod will now be like this. Note that the force, this one acts upwards to the top plate, this one acts upwards to the bottom plate. So it means the rod is going to be vertical, with A next to the top plate and B next to the bottom plate. So we can say to be vertically aligned. Vertically aligned with A at the top next to the positive plate, and B at the bottom. Next to the negative plate. So that is because the question was state and explain the position of the rod when it comes to rest. I think that is will be the position. But maybe just to explain, it is vertical aligned with A at the top, next to the positive plate, and B at the bottom next to the negative plate. This is going to be because there will be no resultant force. There will be no resultant force because now the forces will be acting in the same plane. No resultant force and no resultant torque. Because when they are now vertically aligned, it means their lines of action be passing through each other. Therefore, there will be no resultant force and therefore no resultant torque. Okay, next. So we have an electric field set up, two parallel metal plates in a vacuum as shown. The deflection of an alpha particle as they pass through is shown here. The electric field strength between the plates is reduced. The alpha particles are replaced by beta particles and the deflections have been shown. The deflections are shown here. State one similarity of the electric field shown there. So you notice that they are both in the same direction from up to the bottom. So direction of fields is the same, that is 1. Direction of fields is the same, that is 1. And 2, you see that they are parallel lines, equally spaced. So you could also notice that the fields are uniform or field strengths are constant. So in both cases, the fields are uniform. In both cases, the fields are uniform. Then the electric field strength in figure 7.2 is less than that in figure 7.1. State two methods of reducing electric field strength just by looking at E is equal to V over D. So when we reduce V, electric field strength decreases. When we increase D, it also reduces. So reduce the PD across the plates. Reduce the PD across the plates. Increase the separation of the plates. Increase the separation of the plates. So that one, when I reduce this, it reduces. When I increase D, it still reduces. Next, by reference to the properties of alpha particles and beta particles, suggest 3 reasons for the difference in the deflection. If you are very observant, you have noticed that the alpha particles were deflected following the same path. Yet for beta particles, they are deflected in several paths. And in AS, you must have mentioned that alpha particles have the same discrete energy, yet beta particles have a wide range of energies or velocities. So, number 1, beta has range of velocities or energies, This is as different deflections, as seen from different deflections, as there are different deflections. And alpha all have same energy or same velocity. So when you look at the paths of these two, you notice that beta particles are moving in different paths. yet all alpha particles are following the same path. This is because they have different velocities or different energies. Beta particles have different energies. They have a range of energies, yet all alpha particles have the same velocity or they have the same energy. Number two, I think we all know that alpha is the charge of alpha is opposed to that of beta. Charge of alpha is opposite to charge of beta. And how do we see that? We see that deflections are in opposite directions. Number three, we know that the mass of an alpha particle is 4u and the mass of a beta particle is actually 1/1840u. So it means alpha particles are more massive, and for that reason you notice that the deflection of beta particles is greater compared. There is more deflection of beta particles compared to that of alpha particles, because alpha particles are more massive compared to beta particles. So alpha more massive than beta, as deflection is less, even if the field strength is greater. So this is as deflection is less for greater field strength. So that is that particular question. Because alpha particles are more massive, their deflection is very small compared to that of beta particles, which are easily deflected because they are lighter. Next, a uniform electric field is produced between two parallel metal plates. The electric field strength is given as that. The PED between the plates is given as that. Calculate the separation of the plates. So from E is equal to V over D, then it implies that D is going to be equal to V divided by E. When I substitute, this will be 350 divided by 1.4 times 10 power 4. And when I press my calculator, this gives me 0.025. A nucleus of mass 8.3 times 10 power negative 27 kilograms is now placed in the electric field. The electric force acting on the nucleus is 6.7 times 10 power negative 15 newtons. Calculate the charge on the nucleus in terms of E. Calculate the charge. So we know that E is equal to the force acting on a unit positive charge. So Q is going to be equal to F, which is 6.7 times 10 power negative 15 divided by 1.4 times 10 power 4. That is what we had as E. And this is giving me so this is giving me a 4.8 times 10 power negative 19 coulombs, but they want the answer in terms of E. So charge in terms of E is going to be 4.8 times 10 power negative 19 divided by 1.6 times 10 power negative 19. Since 1 is 1.6 times 10 power negative 19, and when you divide, this gives you 3E. So the answer here is 3. Then calculate the mass in U. Of course, mass is going to be equal to the mass is that in kilograms, so we shall just change it in U. So that will be 8.3 times 10 power negative 27 divide by 1.66 times 10 power negative 27, and when you press your calculator, so this is giving me approximately 5.0 U, 5.0 U or 5 U. Then use your answer in B and B Roman 2 to determine the number of neutrons in the nucleus. So for this nucleus X, this is going to be the mass number, this is going to be the mass in U, and 3 will be the charge, 3e. So that means the number of neutrons will be 5 minus 3, which gives us 2. So the answer there is going to be 2. Okay. Two vertical metal plates are separated by a distance d in a vacuum. This has been shown in the diagram. The PD between the plates is V. A nucleus with a charge positive Q is initially at rest on plate X. The nucleus is accelerated by the uniform electric field from plate X along a horizontal path to plate Y. State an expression in terms of sum or all of d, Q, and V for the magnitude of electric field strength. So E is V over D, so this is automatically V divided by D. Then the magnitude of the electric force, F is QE. F is QE. Force is charge times electric field strength, which will be equal to charge times V over D. So this is Q V over D, because we want to state in terms of only those ones. Kinetic energy is the same as the work done. Therefore, kinetic energy is going to be charge times accelerating PD. So this is Q times V. State the change, if any, in the kinetic energy of the nucleus on reaching plate Y when the following separate changes are made. Number 1, the distance d is halved, but the PdV remains the same. The distance d is halved, but the PdV remains the same. We are looking at the kinetic energy. Kinetic energy is depending on V. V is remaining the same, so here there will be no change. The nucleus is replaced by a different nucleus that is an isotope of the original. Of course, isotopes are nuclei with the same proton number. So it means, and remember, proton number is the one which determines the charge. So since it is the same proton number, so it means Q is the same, even though the number of neutrons is different. So if Q is the same and V has not changed, then here there is also no change. There is no change. Okay, next. The figure shows an electron in an electric field in a vacuum at an instant when the electron is stationary. So the electron is stationary. On the figure, draw an arrow to show the direction of the electric force on the stationary electron. Remember, a negatively charged particle experiences a force in the opposite direction to the field. Therefore, the force due to the electric field must be in this direction here. If the electric field causes the electron to move from its initial position, describe and explain the acceleration of the electron due to the field as the electron moves through the field. Because the force is in that direction, they said the electric field causes the electron to move from its initial position. Describe the electron, the acceleration of the electron. First of all, the force is in the correct direction. There's a resultant acceleration in that direction. But you notice that the field lines are getting closer. That means the resultant, that the field strength is increasing. The resultant force is increasing, so the acceleration must be increasing. So we can say the field strength is increasing electric field strength increases. How do we see that? The lines are getting closer. And if the electric field strength increases, it means the force increases. And if the force increases, remember force is equal to mass times acceleration. So the acceleration increases. The acceleration increases. E is equal to F over charge, or MA over charge. So the electric field strength is increasing. So the force must be increasing, the acceleration must be increasing. The stationary alpha particle is now placed in the same electric field at the same initial position that was occupied by the electron. Note that it is stationary. Compare the initial electric force acting on the alpha particle with the initial electric force that acted on the electron. Number one, the alpha and the electron have opposite signs of charge. Therefore, the forces on them must be in opposite directions. So we can say that the force on the alpha particle is in opposite directions. Is in opposite direction is in opposite direction to the force on the electron because they have opposite charges. Number two, note that the charge on an alpha particle is twice E, yet the charge of an electron is E. So it means the force on an alpha particle is twice in magnitude as compared to the force on the electron. So the force, remember force is equal to Q times E. So it is twice. The force on alpha particle is twice in magnitude to the force on the electron. Okay. The force on an alpha particle is twice in magnitude to the force on the electron. Two horizontal metal plates are separated by a distance 2 centimeters in a vacuum as shown. The top plate is at electric potential 180. The bottom plate is at 120. That means the difference in potential is going to be 180 minus negative 120, which gives us 300. Determine the magnitude of the electric field strength between the plates. So we know that E is equal to V over D, where V is potential difference. That will be 300 divided by the separation. The separation was 2 centimeters, so this will be 2 times 10 power negative 3. 3 is divisible by 2, so that is 1.5 times 10 power 4 newtons per coulomb. State the direction of the electric field. We look at the diagram. The direction, so the field lines should originate from high potential to low potential. So state the direction of the electric field, that is vertically downwards. Vertically downwards. An uncharged atom of uranium that has a change made to its number of orbital electrons. This causes the atom to change into a new particle ion that has an overall charge of positive 2e. Note that was an uncharged atom. That means the total number of electrons was the same as the total number of protons. Now, if it turns into a particle ion X, that has an overall charge of positive 2e, it means it has two more protons than the electrons. So it means the number of electrons should be less than this, so the number of electrons will be 90. Of course, the number of protons will remain 92. Two more protons higher than the number of electrons. The number of neutrons will still be 238 minus 92, which gives us 146. So it is just two electrons. The number of electrons is less than the number of protons by just two, because initially it was uncharged. Total charge was initially 0. Uncharged means the total number of protons was initially the same as total number of electrons. Okay. The particle ion X is in the electric field in A at a point midway between the plates. Determine the magnitude of the electric force. Electric force is given by charge times electric field strength. 1.5 times 10 power 4, that was E, times the charge. It is because the charge is positive 2, so this will be 2 times 1.60 times 10 power negative 19. Okay, so when I press my calculator, so this is giving me 4.8 times 10 power negative 15 newtons. The potential difference is applied between two horizontal metal plates that are a distance 6 millimeters apart in a vacuum, as shown here. So this is at zero potential, this is at negative 450 volts. The top plate has that potential, the bottom plate is earthed. Assume that there is a uniform electric field produced between the plates. A radioactive source emits beta minus. It emits beta minus. So if it emits beta minus, chances are high that the force on the beta minus particle is downwards. So they are actually being slowed down, because negatively charged particles experience a force in the opposite direction to the field. The field lines are from high potential to low potential, and the negatively charged particle experiences a force in the opposite direction to the field lines or to the electric field. Determine the magnitude and direction of the electric force acting on the beta minus particle. That one we have already said the direction is downwards, towards high potential, so it is downwards. Then the only challenge we have is the magnitude of the force. So force is equal to charge times electric field strength. And the charge, this will be charge times V over D. So the charge it is a beta particle, 1.6 times 10 power negative 19. Potential difference is 0 minus negative 450, so that is 450 volts. Divide by the separation of the plates, which was 6 millimeters, so this will be 6 times 10 power negative 3. So this is giving me 1.2 times 10 power negative 14. Yes, 1.2 times 10 power negative 14 newtons. Then work done. For work done, we have already now noticed work done. Work done is charge times potential, or it can be work done is force times distance, which can be charge times electric field strength, charge times electric field strength times distance, depending on what you have. But since we already have the force, so the work done will be 1.2 times 10 power negative 14, then times 6.0 times 10 power negative 3. Note that it is moving in the opposite direction to the force it experiences. So if you want, you can put a negative. When I press my calculator, so this is giving me 7.2 times 10 power negative 17. Alternatively, you can also think of work done as being charge times accelerating PD, where the charge is 1.6 times 10 power negative 19, and the PD is 450 joules. It will give you the same thing. The beta minus particle is emitted from the source with kinetic energy that calculate its speed. That is easy. Kinetic energy is a half mv squared. So the speed is going to be 2 times the kinetic energy, 3.4 times 10 power negative 16 divided by the mass, 9.11 times 10 power negative 31 under the square root. So this is giving me 2.7 times 10 power 7 meters per second. A small charged glass bead of weight 5.4 times 10 power negative 15 newtons is initially at rest at point A in a vacuum. The bead then falls through a uniform horizontal electric field. The field is horizontal. If the field is horizontal, then the plates must be vertical. The plates must be vertical if the field is horizontal. Part A, of course, the electric field strength is given as this. The charge on the bead is negative that. Describe how the two plates could be used to produce the electric field. One, since the plates the field is horizontal, the plates must be vertical because the electric field is always perpendicular to the plates in a uniform field. So one, we can comfortably agree that the two plates are vertical. The two plates are vertical and separated. They should be separated. If they are overlapping, then there is no difference in potential. And separated with the left plate positively charged Why should the left plate be positively charged? Uh, this particle is experiencing two forces, if I can put it. Its weight is vertically downwards. The force due to the electric field must be in this direction because the resultant is here. Since it is negatively charged, the negatively charged particle experiences a force in the opposite direction to the field. So I am saying if the particle is moving towards this side, then the field is the other way around. The field should be the other way around. So I am saying the two plates are vertical and separated with the left plate positively charged and the left and the right plate negatively charged. And the right plate negatively charged, but it can also be earthed. In other words, the plate on the right should be the one with the lower potential, the plate on the left should be high potential. This will be positive, the other one will be negative, so that if the field is in that direction, the negatively charged particle experiences a force towards high potential. Okay, determine the magnitude of the electric force. So the electric force F is given by the charge times electric field strength. So this will be, the charge was 3.7 times 10 power negative 9. The electric field strength is 1.3 times 10 power 4. And when I press my calculator, so this is 4.8 times 10 power negative 5 newtons. Use your answer in B and the weight of the bead to show that the resultant force acting on it is that. So the weight is vertically downwards, the electric force is in that direction, the resultant is there. So that is Pythagoras theorem. So the resultant force F is going to be the square root of 4.8 times 10 power negative 5 squared plus 5.4. I think the other one is 5. What 4.8 was the electric force. What is the weight? 5.4. The weight is 5.4 times 10 power negative 5 squared. When I press my calculator, pressing the calculator gives me 7.2 times 10 power negative 5 newtons. Explain why the resultant force on the bead of this is constant as the bead moves. Of course, we have seen there are two forces acting. The electric force will be constant because the field is uniform. Number two, the weight does not just change. The weight will be constant. So the weight is constant. The weight is constant. That's number one. The electric force is also constant. The electric force is constant because the field strength is constant. So it means the resultant force must also be, if the two forces, the weight and the electric force, are constant, it means the resultant force must also be constant. So the resultant force must also be constant. Calculate the magnitude of the acceleration of the bead along the path AB. Acceleration. So first of all, we must seek for, we have the resultant force. Acceleration is equal to the resultant force divided by the mass. All that we don't have is the mass. But the mass is going to be equal to the weight divided by g, which will be 5.4 times 10 power negative 5 divided by 9.81. That is the mass. So it means the acceleration is going to be F. F is 7.2 times 10 power negative 5 divided by the mass. So the 9.81 will go up, and in the denominator I will have 5.4 times 10 power negative 5. Pressing the calculator, this is giving me 13 meters per second squared. 13 meters per second squared. But next, the path AB has a length of that. Use your answer in Roman 1 to determine the speed of the bead at point B. So if we are using the acceleration and they've given us the displacement, then we shall simply use the equations of motion. So v squared is equal to u squared plus 2as. It started from rest. So v squared is going to be 2 times the acceleration, which is 13, times s, which is 0.58. And I press the calculator very fast. So this is 3.9. 3.9. Okay. Next. A spherical oil droplet. A spherical oil drop has this radius. The density of the drop is that. Show that the mass of the oil is that. I think that is an easy question. Mass is equal to density times volume. The density is 940. The volume, we assume it is spherical. It is actually spherical. Volume of a sphere is 4/3 pi radius cubed, so that would be 1.2 times 10 power negative 6, and this is raised to power 3. When you press your calculator, I'm very certain you get 6.8 times 10 power negative 15 kilograms. Part 2. The oil drop is charged. Explain why it is impossible for the magnitude of charge to be that. I think we are now aware that the minimum charge on a drop should be 1.6 times 10 power negative 19 coulombs. So this would be not possible. The minimum charge, because charge is a multiple of the elementary charge, so the minimum charge on the drop is 1.6 times 10 power negative 19 coulombs. So it is not possible. So it's not possible. The charged oil drop is in a vacuum between the two horizontal metal plates as illustrated in the figure below. Okay. The plates are separated by that distance. The electric field between the plates is uniform and has a field strength that. The oil drop moves vertically downwards with a constant speed. Note that constant speed means resultant force is 0. Calculate the PD between the plates. So V is going to be E times D. So V is 2.1, E is 2.1 times 10 power 5. The separation of the plates is 8.0 times 10 power negative 13. Negative 3, not 13. So when I press my calculator, so this is giving me 1.7 times 10 power 3 volts. Explain how the motion of the oil drop shows that it is in equilibrium. So constant velocity means no resultant force, that's in equilibrium. Constant velocity means or implies no resultant force or no acceleration, thus in equilibrium. Okay, so that is our part. Okay, determine the charge on the oil drop. If it is moving at constant speed, there are two forces. The weight is acting downwards, Fg is m times g, and there must be a force acting in the opposite direction, which is the force due to the electric field, that is Q times E. So we have that mg should be equal to E times Q, where the charge should therefore be mg divided by E. And when we substitute, the mass was 6.8 times 10 power negative 15 times g 9.81 divided by E was 2.1 times 10 power 5. Answer. So calculating the answer, I get 3.2 times 10 power negative 19 coulombs. How about the sign? Let's go back here. So the weight is downwards. The force due to the electric field is upwards. But note that the upper plate is positive. The only charge which can experience a force due to the electric field or in the opposite direction to the field or towards the positive plate must be a negative charge. So the sign of this must be negative. So the sign here is negative. Okay. The magnitude of the potential difference between the plates in V is decreased. V is decreased. That means E has been decreased. If E is decreased, F due to the electric field has been decreased. Explain why the oil drop accelerates downwards. So the electric force decreases because it depends on the PD. Electric force is equal to Q times E, which is QV over D. Because V is reduced, the electric force has been reduced. So the electric force decreases, which now means that the weight is greater than the electric force. So the resultant acts downwards. So the resultant is acting downwards. That's why it is going to move downwards or accelerate downwards. Describe the change to the pattern of the field lines or lines of force representing a uniform field as the potential difference decreases. When V decreases, E decreases. That means the field lines move further apart. So the separation increases. So the separation of field lines increases. The separation of field lines increases. Next, two types of force, X and Y, can act on an oil drop when it is in air, but cannot act on an oil drop when it is in the vacuum. So when it is in air, there are several forces acting. Of course, the weight acts downwards, whether there is a vacuum or not. There is also in air, it has upthrust. There is upthrust. There is also air resistance. Air resistance if it is in air. So they are saying two types of force, X and Y, can act on an oil drop when it is in air, but cannot act on an oil drop when it is in a vacuum. So in a vacuum, we don't expect air resistance. We don't also, since there will be no air resistance, we shall also not expect upthrust. So the two forces must be upthrust and air resistance. Because in a vacuum, the weight will still be there because it's depending on gravity. But then force X can act on an oil drop when it is stationary. That is automatically going to be the upthrust. When it is stationary, that is the upthrust force because it cannot act when it is moving. No, it can act on the oil drop when it is stationary or even when it is moving. Then the force Y can only act on an oil drop when it is moving, that is friction. So that is air resistance. Air resistance tends to oppose the relative motion. So that is air resistance, or sometimes called viscous force, or it is sometimes called just drag. Okay, next. State what is meant by a field line. I think we have already defined a field line. A field line is a line which gives the direction in which a free positive charge would move. That is for an electric field. The line which gives the direction in which a free positive charge will move. Line which gives the direction in which a free positive charge will move. That is an electric field line. An electric field has two different regions, X and Y. The field strength of X is less than the field that of in Y. Describe a difference between the pattern of field lines of force in X and Y. Since X is less, then the field lines must be farther apart. Since Y is greater, the lines are closer together. So we can say lines in Y. The lines in Y are closer together than those in X. Or the lines in X are farther apart than those in Y because the field strength is inversely proportional to the separation. If the separation is smaller, the field strength is higher. And if the separation is greater, the field strength is smaller. A particle P has mass 0.15 U and charge negative E, where E is the elementary charge. A particle P and an alpha particle are in the same uniform electric field. Calculate the ratio acceleration of the particle P. So I will say acceleration of P divided by acceleration of the alpha particle. Note that I want you to note that force is equal to mass times acceleration, which is Q times E. So it means the acceleration is QE divided by M. So for an alpha particle, acceleration of P divided by acceleration of alpha is equal to, for P, it will be charge of P, which is E. Electric field strength is the same. The mass of P is 0.15 U divided by, I get the reciprocal. For alpha, the mass is 4U divided by the charge of alpha is twice E times the electric field strength. And you realize that this is going to give us 4 over 0.15 times 2. And this is giving me 13.3 or approximately 13. So that is the ratio. Okay, last but not least, two vertical metal plates in a vacuum are separated by a distance 0.12 meters. Each plate has a length of 2.0 meters. The potential difference between the plates is 900 volts. The electric field between the plates is uniform. A negatively charged sand particle is released from rest at point X, which is a horizontal distance of 0.08 from the top of the positively charged plate. So X is 0.08 from the other plate on the right. The particle then travels in a straight line and collides with the positively charged plate at its lowest point. Describe the pattern of the field lines of force between the plates. So since the plates are vertical, the field lines are horizontal. That's number one. And note that the field lines originate from high potential to low potential. So the field lines are going to originate from the other side, from the right to the left. So we shall say the field lines are equally spaced, or we can say equally spaced, straight, horizontal lines from the one of positive 900 volts to the zero volt plate. They are equally spaced straight lines, straight horizontal lines from positive 900 volts plate to the 0 volts plate. So those are the field lines. They are equally spaced. Because the plates are vertical, the field lines are actually going to be horizontal. State the name of the two forces acting on the particle as it moves from X to Y. First of all, there is its weight. If it is in a vacuum, then there is also only the electric force. Weight and the electric force. Weight and the electric force, or gravitational force and electric force. By considering vertical motion of the sand particle, show that the time taken for the particle to move from X to Y is 0.64. We are going to use S. S is equal to ut plus a half at squared. When I consider vertical motion, initial velocity is 0, remember? So it means S is given as 2.0. Considering vertical motion, S vertical displacement is going to be the length of the plates, which is 2.0. Initial velocity, remember, is 0, so this will be a half times 9.81 because I'm considering vertical times t squared, which implies that t is equal to, that is 4 divided by 9.81, which is 0.64 seconds. Calculate the horizontal component of the acceleration of the particle. Now we are in the horizontal. I will still use S is equal to ut plus a half at squared. In the horizontal, remember it starts at a distance of 0.808 from the right hand plate. So S is this distance here, 0.08 meters. So 0.08 meters will be equal to, remember it is initial at rest, so this will be a half times acceleration, which I want to find. Of course, the time will be the same, 0.64. When I press my calculator, I obtain 0.39. Calculate the magnitude of the electric field strength. Of course, E is equal to change in potential difference over distance, and this was 900, or PD was 900 over the separation of the plates. The separation of the plates is 0.12. So this is going to be 0.12. Now I press my calculator. So this is giving me 750, or 7.5 times 10 power 3. No, 7,500. The sand particle has mass m and charge q. Use your answer in D and E to determine the ratio q over m. So we know that the force is mass times acceleration. That's number one. And we also know that this will be the same as charge times electric field strength. So we want q over m. This will be equal to acceleration over electric field strength. So this will be 0.39, that is the acceleration, divided by electric field strength, 7.5 times 10 power 3. When I press my calculator here, this is giving me 5.2 times 10 power negative 5 coulombs per kilogram. That is the ratio. Of course, Q over M is called a specific charge. Lastly, another particle has a small magnitude of the ratio Q over M than the sand particle. The particle is also released from point X, the same point as before. For the movement of this particle, state the effect, if any, of the decreased magnitude of the ratio on the vertical component of the acceleration. Of course, the vertical component of the acceleration is actually acceleration due to gravity. Therefore, it means there is no effect. there is no effect. The acceleration due to gravity is not depending on the charge to mass ratio. So there is no effect. Number two, the horizontal component of the acceleration. Note that from this formula here, from this expression, we have seen that acceleration over E is equal to Q over M. Now this is decreased. When Q over M is decreased, of course, the acceleration also decreases. So this one also decreases, or it becomes smaller. Okay, so that is the end of electric fields 1. That is the first part. You notice that we have been dealing with a uniform field. In lesson 3, we shall deal with a non-uniform field and basically point charges. Do not forget to subscribe, share, and like the video. Do not forget to download the document attached so that you use it as your practicing guide. Thank you, thank you, thank you, thank you. Bye bye.